Hello, right, there's a few more circuit type questions. We've got a domestic fan heater of 2.6 kilowatts when connected to 230 volts main supply, and that's our maximum power input. It consists of two heating elements, which are resistors rated at 1.5 kilowatts and 1 kilowatt, and a motor rated at 100 watts, right? So that all adds up to the 2.6 kilowatts that we've got here. And then there's three switches, which are going to be, I'd imagine, to turn on the motor and each of the heating elements. Show that the resistance of the 1.5 kilowatt heating element is about 35 ohms. Right, so it doesn't explicitly say in this description how they've arranged all of these elements. But whenever you have things like this, they all need to be in parallel. They all need to be having this 230 volt potential difference across them. If you put all of these elements in series, first of all, the switches wouldn't work very well, because if everything's in series, you only need one switch. And also, if they're all in series, you're not going to be getting the 230 volt potential difference across them. You know, you put these two heating elements, these two resistors in series, well, why have two resistors? You might as well just have one of them, because they're just going to add up in a regular, you know, if you've got 35 ohms and 40 ohms or something like that, they're just going to add up to be 75 ohms. Well, you might as well just have a 75 ohm element if they're in series, because they're always going to just be both on or both off. There's no point having two elements, so they must be in parallel, so you've got control of having one or both elements on, and they're both getting the potential difference of 230 volts. So what that means for this calculation is, when we do our power is V squared over R, because we want to work out R, and we've got P and we've got V, so that's the one we're going to go for. It means we can use a V of 230 volts. So let's rearrange that to say the resistance is going to be P V squared over P. So that is 230 squared divided by, which one are we doing? The 1500 watts. So actually, we can probably do this without a calculator. So let's go to two zeros on the top, two zeros on the bottom. So we've got 23 squared over 15, which is 23 times 23 over 15, which is going to be 23 times 1 plus 8 over 15. This is where fractions really come out here. So we've got 23, 8 23s are 184 over 15. 15's into 184. That is 12 and 4/15. So we're now up to 35 plus and 4/15. The 15th is what, 6.6%. So we're going to get 35.26 recurring. So 35.26 recurring. So let's just call that 35.3 ohms. There you go. A nice bit of mental maths to do on all of that, although it's probably used up more screen than I would like, and I'm going to probably complain about that when I get to the bottom of the page. Anyway, the next part, the 1.5 kilowatt heating element is made from wire across sectional area, right? We're getting resistivity, right? We're going into the resistivity equation. We need to calculate the length of the wire. So rearranging the resistivity equation for length, we're going to get that it's R times A divided by rho. So yeah, all we're doing is typing in numbers on all of this. I'm certainly not going to be doing these with a 7.8 and a 1.1. I'm going to do this in the calculator. So that's just, I'm tapping it in now, 2.5 meters. Yeah, we're just putting in this value of R, this value of A, and this value of rho into here. We get 2.5 meters to two significant figures. With only the first switch closed, the fan rotates. Yep, close the second switch and we get the 1.5 kilowatts. Close the third switch, we get 2.5 kilowatts. Elements will not heat up unless the fan is switched on, and we cannot just have the small element. Complete the circuit diagram showing the fan, the heating elements, and the switches. Right, well, we know that they're all in parallel. So let's put these in first of all. So we've got the motor, we've got the two resistors, It's just going to be a case of where to put the switches. We can put all the switches up the top. So we need, nothing's going to come on unless we got the switch that turns on the motor. The motor comes on first. So if we had a switch there, then that will turn the motor on. But we need to have the other switches in each branch. So if we got a switch there, then the motor will come on when we close the first one, but this isn't going to turn on either of the heating elements. Then we flick that switch and it's going to turn on the middle component, and then we have another switch at the end. So you can just see we've got this cascade here. As you flick each switch, we're going to be getting one thing turning on at a time. And it doesn't matter if you close the second or the third switch before you've closed the first one, because the first one's like the master switch, isn't it? So this is going to be the 1.5 kilowatts, and that's going to be the 1.0 kilowatts. So yeah, this fits with, again, what I was saying earlier on about why we need all these things in parallel. You wouldn't have this control with 3 switches if you tried to put them all in series. Both heating elements are made of wire of the same resistivity and length. Explain why, without calculation, the diameter D of the 1 kilowatt heater wire must be less than the diameter D of the 1.5 kilowatt heater wire. Okay, so this is coming back to actually our power equation. So you want to start off saying, well, the power is equal to V squared over R. So you can say if P is lower, then R must be higher for the same V, because we know we've got the same potential difference over these. So if P is lower, R must be higher, which then means, so then we can go over to our R equals, so this is our resistivity thing, so rho L over A. So if R is higher, then we can say off of that that A is lower for a constant rho and L, which is what they've given us in the question, I believe. So they've got, yeah, the same resistivity and length. So we've got a constant rho and L, which means we've just got that nice chain there. So doing that, you know, write out the formula, say the consequence, write out the next formula, say the next consequence. Show that D is approximately 0.8 of the diameter of the other one. Right, so the small one has got 0.8 the diameter of the other one. Right, well, we can just run through these equations then off of here, because we're saying that yeah, I mean, of course, this is going to have quite a lot of steps in it, actually, going through all of these bits. So we've got the first of all, so A is proportional to D squared. That's the sort of thing that we want to say, first of all. So the cross-sectional area is proportional to the square of the diameter. So if we've got the same resistivity and length as we've got here, we can then use this and say that R times A, so R1 times A1 is going to be equal to R2 times D2, because we know that rho times L is the same for both of the resistors. So that means that we've got R1 times D1 squared is equal to R2 times D2 squared for the two resistors. Then we can replace that with the stuff that we've got here. So we know that R is V squared over P, and they're the same V squareds. So we've got V squared over P1 times D1 squared is equal to V squared over P2 times D2 squared. We can cancel those V squareds. Excuse me. What one were we trying to work out? All right, it doesn't matter which way round we're going to do it. So let's say that D1 is D. So we can say let D1 equal D, which is what we've got there. D2 equals little d. That's what we've got from the question. So we want to work out what little d is. So we're saying that little d squared is going to be equal to d squared times P2 over P1, which is, so our P2, we can also put in here, P1 was our, so that's the big one, isn't it? So that's the 1.5 kilowatts. P2 is 1.0 kilowatts. So we've got D squared 1 over 1.5. So we just need to do the square root of that. So that leaves us with little d is equal to d times the square root of 2/3, which is, yeah, that comes out 0.8d. So yeah, there's quite a lot in that, but I like that though, because it follows on from the previous part where again you're doing that. We're not putting numbers into this until the very end, but we're just continuing to explore these two equations by just getting them to, well, subbing these r's in, removing the r's, because we're not talking about that. It's not in the question. We don't have r's in here. We can cancel so many of these things. We want to combine these two formulae and eliminate everything except for D and P, which is essentially where I've got to there, because they're the bits of information that they've given us in the question. Right, part D, right, something looks as though it's gone wrong here and me putting this together. Circle the correct fuse for the plug of this appliance and the values below, and the values below clearly haven't come out as they should have done. But we're going to get the highest current when all the switches are closed. And you can think about that in two ways when you're looking at a circuit. You've got, well, if everything is connected up, if everything's running, we're drawing more energy out here because we've got both heating elements and the motor on. So we want to get more energy out. We need to draw more current in order to do it. So you're going to get maximum current when everything is closed. Or you could say, well, every time we close a switch, we're adding another branch to our parallel set of components. And every time you add a parallel branch, you're reducing the resistance. If we got a fixed voltage and we're reducing resistance, we must be increasing the current because of our V equals IR. So two different ways of thinking about how a circuit works, either in terms of energy or in terms of resistance to current flow. So it's useful to get that sort of mindset. So what is our maximum current going to be? Our I max is when we've got full power. So I max is going to be our 2,600 watts divided by our voltage. Cancel that. So we've got 10, 11 would take us up to 253. So we got 11 and then 7/23. So it's going to be about 11.3 amps is our maximum current. So we're going to want a fuse, which is going to be, say, a 13 amp, 14 amp fuse. So let's say a 13 amp fuse, because you want something which is a bit bigger than the maximum current, but not massively bigger than the maximum current. So, yeah, that's covered that one. I'd imagine that would have been one of these. Let's say it's in there, circled out. Right, last part. E, define the kilowatt hour. Right, so the kilowatt hour is a unit of energy, which is the energy of a 1 kilowatt supply for 1 hour. So you can put it that way. You can actually just say as well, because you could say, well, unit of energy, which is equal to 1,000, that's our 1 kilowatt, times the number of seconds in an hour, which is equal to 3.6 megajoules. So it is just a unit of energy. You know, a lot of people, when they're first coming across kilowatt hours, they're thinking about kilowatts per hour. There's a real habit of putting pers in things when they're not actually there. You know, think of the same with resistivity. This isn't ohms per meter, it's ohm meters. This is kilowatt hours. So if you want to, you can see how we're then getting energy there. Kilowatts. So that is kilojoules per second. If you then multiply by the number of seconds, you're then getting kilojoules. Okay, here I've ended up writing it in megajoules, but you can see how you get energy out of it. You multiply wattage by time, you get an energy. Right, calculate to the nearest penny the cost of using the heater for 4 hours with only one of the heating elements. So when we've got one heating element on, that means we flick that switch and that switch. So we've got the heating element plus the motor. So we're doing 1.6, not 2.6, 1.6 kilowatts for 4 hours. So the number of kilowatt hours we're going to get is just multiplying these things together. So we've got 4 times 1.6, that's our kilowatt hours, and they've told us that it is 18p per kilowatt hour. So we need to multiply that by 18p, and that will be the number of pence that we've got. So what's that? 6.4 times 18p. 6 18p's is 108. 0.4, so 4 1.8 is 7.2. So that is 115.2, so 115 pence to the nearest penny. Yeah, that's a really nice question, that is. I mean, there's so much in it, but yeah, I like that. Let's move on to the next one. Hopefully they're going to be a little bit quicker. My mouse has disappeared. There we go, back again. IV characteristic for a 6-volt 1.5 watt filament lamp. Okay, so we've got the usual non-ohmic profile that we get these filament lamps, where our gradient, which is 1 over the resistance, so the gradient's decreasing, which is showing how the resistance is going up. This is probably what they're going to be asking us about. State how this shows that the filament lamp does not obey Ohm's law. So, well, we can say it's not a straight line going through the origin. The gradient is changing, so resistance is not constant. That's the main thing we want out of this. Yes, the gradient, I'm not going to write it out, you just say that the gradient is not constant, so the resistance is not constant, the resistance of the filament. Explain how this shows that the resistance of the filament lamp is about 10 ohms when the current is between 0 and 50 milliamps. Right, okay, these are always annoying trying to go through these. How many lines? 1, 2, 3, 4, 5. Right, so that is our 50 milliamps. And right, so that's going up to there. All right, that's pretty much halfway up. Yeah, so we can see there. So this portion here, we're saying that our resistance is equal to 1 over the gradient, which in this case, so we want the change in X over the change in Y. So the change in X, we've got half a volt here, and we're dividing that by the change in Y, which is this 50 milliamps. So 50 milliamps is 0.05 amps. So that gives us 10 ohms. And it's nearly a straight line, so that's what they're going for on this. I mean, it's like that with these curves. If you pick any little bit, or even when you get a bit higher up here, you can pick quite a big bit, and it looks fairly straight. Explain why the resistance of the filament lamp is much larger at 6 volts. So this is explaining why here. So we've got emphasis on why. It's not asking us to calculate what the resistance is. It wants us to explain it. So we're going to say that as the current increases through the filament, it's always good to put your prepositions in on circuit stuff. So PDs go across, currents go through. As I goes up through filament, the temperature will go up. And then we can say as temperature goes up, the resistance goes up. Therefore, gradient will go down, which is what we're seeing here. So it's another one of those chains going on. This happens, so that happens. And as that happens, this happens. And that's how we see it in the graph. Wonderful. This is, yes, it continues on the next page, as these things usually do when they've got the big graphs there. Student designs a circuit for a night light using a filament lamp of part A, okay, and a LDR. There's that setup. Right, so the LDR, as the light is shining or not on the LDR, this is changing the resistance of this branch, depending on how much light is shining on the LDR. And that is going to change the potential difference across the filament lamp. So it's telling us that it's 1 ohm in daylight and 1000 ohms in the dark. So that's quite a big variation. Show that the circuit will cause the lamp to be off in the day and on at night, as long as the light from the lamp does not shine on the LDR. Right, so one thing that throws people off with these is they get fixated on trying to work out an exact resistance for the two components in parallel, but we don't really need to do that. It's actually quite hard to do, but we don't really care, because we can see that we got variation here in the LDR in resistance, which is pretty big. You know, that's going from 1 ohm up to 1000 ohms there. We saw on the previous slide in the first part of the question that the variation in the resistance of the filament lamp is going from 10 ohms to 25 ohms. Now, when you've got a parallel pair like this, the current is, well, it's going to favour going down the lower resistance path, and you're going to end up getting slightly lower than the lowest resistance if you've got this big difference. You think if you were going to do a the 1 over R1 plus 1 over R2 and then take the reciprocal thing for working out the resistance of the pair of parallel resistors, well, you're not going to get much of an effect of having a 10 ohm resistor in parallel with a 1 ohm one. It's going to come out pretty close to 1 ohm. And similarly with these ones, it's going to come out pretty close to a 25 ohm resistor, because sticking in something really high resistance in parallel doesn't have that much effect on the current and than the PD. So we can just say, well, it's pretty close to these. Okay, it's not going to be exactly these. It's not going to be exactly 1 ohm. It's not going to be exactly 25 ohms when they're put in parallel. It's going to be a little bit less than 1 and a little bit less than 25. But it's as good as for if we're going to work out whether the light comes on or not, if this filament's going to actually start powering up. So if we then say, okay, well, in daytime, we can say that the resistance in parallel is going to be roughly equal to 1 ohm, even if it's, or slightly less than 1 ohm, but roughly equal to 1 ohm. So we'll just go with that. We've now got a potential divider set up as we have in these circuits. We got a total resistance of 26 ohms. So we're going to get 25 over 26 times 12 is going to be the PD across this resistor. And then across the lamp, we're going to get the other 26 multiplied by 12. So we haven't even got half a volt across the filament lamp during the day. So that is less than 0.5 volts. Therefore, the lamp is off. We can then look at night and say, well, at night, our parallel is going to be around about 25 ohms, because this resistance isn't really offering us much as a viable alternative for the current in the parallel branch. Still mostly going to be going through the 25 ohm section. So if we've got 25 ohms, we're now split 25, 25. We're going to get 6 volts over each section of this circuit, 6 volts over the fixed resistor and then 6 volts over the LDR and also over the filament lamp. So that means that the lamp is going to come on. So don't get fixated on, oh yeah, well, what exactly is the resistance, and what's our potential difference to 3 decimal places or something daft. You just need to get something pretty close, and that's what these LDRs are really doing. They're giving either this is the path we're going to be taking, we're going to go down this low resistance route, in which case we're just not getting anything going through the bulb, or we're blocking it off and saying, right, everyone's got to go through the bulb now. That's our only way of powering this thing up. It's the only way of going through is because we've blocked this off. It's just like having a tap turning on or off on the LDR branch. So again, those different ways of thinking about what circuits are doing. It's like, where do you want your current to flow? Do you want the current to go through the filament lamp, in which case you need high resistance here? Or do you want the current to go through the LDR, in which case you want low resistance there? It's just controlling the flow, as I talk about all the time in these circuit videos. Right, so let's finish that question. Last one in this set. All right, we got more. We got an LED, if I can say it, LED, a light emitting diode rather than an LDR. So we got the IV characteristic there. Data for plotting the IV characteristic is collected using components shown in figure 4.2. Well, they've got nothing in that figure that's collecting anything. There's no voltmeter or ammeter. By drawing on that figure, complete the circuit showing how you connect the 2 meters needed. Okay, right, so we've got to put them in. So we're going to want an ammeter, which we're going to stick in series, and then we're going to want to have a voltmeter. So the voltmeter, this is just for the LED, so we just whap that around there. You don't want to include the other resistor in it, because obviously you're just measuring then what the EMF is. So we'll have that. When the current in the circuit is 20 milliamps, right? That's the top of our y-axis there. Calculate the terminal potential difference across the supply. Right, so we need then, we need to know what the resistance will be so we can see how much of the voltage it's taken. We know that we've got 4 volts here, but what is the resistance? Because we need to know what voltage we've then got across the fixed resistor. So our resistance at that point is going to be V over I, which is 4 divided by our 20 milliamps. So that is going to be 200 when we divide that through. So that means if we've got 200 ohms here for 4 volts and we've got 100 ohms there, well, we must have 2 volts, which means our EMF is going to be equal to 6 volts. That's good. Part B. The energy of each photon emitted by the LED comes from an electron passing through the LED. Yes, we were talking about that earlier on. That's those recombining of the electrons and the holes in the semiconductor of the LED, as I was talking about in the semiconductor video. And when they combine, you're getting a more tightly bound electron because it's gone back into the valence band, and because it's more tightly bound, the energy gets released as a photon, and they're picking those energy gaps so that the emitted photon is the light that we want. We got energy of a blue photon is that. Calculate the energy of a blue photon in electron volts. Right, well, converting to electron volts is pretty easy. We take the energy and we just divide by the 1.6 times 10 to the minus 19. So we've got, what's 1.6 into 4.1? So we've got 2 and 9/16. 2 and 9/16, that's 2.5 and a 16th. 2.5 plus a 16th. A 16th is what, 0.0625. So that's going to be 2.5625. So let's say 2.6 eV. Explain how your answer to that is related to the shape of the curve. Right, this 2.6 EV, so this is the energy that you have to have in the electron that can get released. So this is our threshold voltage. Essentially, you can see here that we're kicking in here around about 2.6. So explain how your answer is related to the shape of the curve. Yeah, so we need our voltage. This is the joules per coulomb. That's if we're just doing voltage. If we're doing electron volts, that's our joules per electron. That's what we're doing by dividing by the charge on the electron. So we're taking the joules per coulomb of charge to the joules per electron as we've got things moving around. So electron volt is joules per electron. So we need a minimum of 2.6 EV on each electron to produce a blue photon. So therefore, our threshold voltage is equal to 2.6 volts. Right, so that's good. Where are we now? I've just done that one. Calculate for a current of 20 milliamps the number of electrons passing through the LED per second. That's easy enough because this is our coulombs per second. So if we want to change from coulombs to electrons, we just divide by charge on the electron again. So we're doing 0.02 divided by 1.6 times 10 to the minus 19. Again, this is all unit stuff if you get stuck on any of this. So you think of your current as being coulombs per second. We want to change this to electrons per second. So if we're wanting to do that, we need to divide by the charge on an electron. So because we're saying that coulombs per electron is equal to the 1.6 times 10 to the minus 19. So if we divide by this, then we're going to end up flipping it and multiplying, so we'll be multiplying by n over c. That's going to cancel the coulombs, and then we got electrons per second. So again, it's just unit analysis. It can be really useful for if you get stuck on these things and what you're meant to be doing with the numbers. So that is, well, let's make that a 2 over 1.6 times 10 to the 17. 2 over 1.6 is 1 over 0. That's 1 1/4, isn't it? So 1.25 times 10 to the 17. They've given us some really nice numbers here. So that's electrons per second. Total energy of the light emitted per second. So this is our, well, this is our number of electrons per second. So we just need to multiply by the energy released by each electron, which is this thing. So we need to multiply these together. So because we know that each electron is producing one photon, each photon is releasing that energy. This is the number of electrons we're getting per second. So our emitted power, energy of light emitted per second, is going to be that multiplied by the 4.1 times 10 to the minus 19. So 1 1/4 4.1s is going to be 5.125 times what we got, 10 to the minus 2, and all of that. So 5.1 times 10 to the minus 2 watts on that. The efficiency of the LED in transforming electric energy into light energy. Well, the actual energy we're pumping into this, the wattage we're actually putting in, so actual wattage, this is at 20 milliamps, so we're up here. Our actual wattage is 0.02, our 20 milliamps, times our 4 volts. So that is 0.08 watts. But we're only getting, we're comparing that to 0.051 watts. So our efficiency is then going to be 0.051 divided by 0.08, which comes out, okay, that's close enough that I think I'm going to want to use a calculator. So we've got 64% on that one. That's good. Last bit of the last question. The energy of a photon emitted by red LED is 2 eV. Right, the current in this LED is 20 milliamps when the PD is 3.4. Draw the IV characteristic on here. Right, so we know we want to end up at our 20 milliamps at 3.4 volts. 1, 2, 3, 4. Which one is it? 1, 2, 3, 4. So that line there. So we want to end up here at our 20 milliamps at 3.4, but we also know our threshold is at 2. So we want to be kicking in about here. So we want a curve that looks more or less the same. So a parallel line to that, but it's just starting at a lower point because there's less energy in the red photons. So it's kicking in that little bit earlier, but we got much the same graph otherwise. Well, that was 3 really, really nice questions. So quite a long video though, but there you go. That's another 3 done.